The integral from, oh, this is Co-17B. Yeah. Day is the 25th of October. From 9 to 81 of the natural log of y to the 8th divided by the square root of 36y. I'm assuming that I'm going to make that a different number for reasons. So if the square root of 36y, it's almost a little too easy. Because what's the square root of 36? So you can totally just write that as 6 times y to the 1/2. But here it's a little bit more challenging to do the right thing. So here's how I would recommend we all rewrite this. I'm going to write this as the integral from 9 to 81. The natural log of y to the 8th we should for sure write as 8 times natural log of y. And we should definitely break this up as the square root of 6 times the square root of y. And then we should pull out the constants. We got 8 over root 6, integral from 9 to 81. And I'm going to write this as y to the negative 1/2 times the natural log of y. If that had been a y to the first in the denominator, I would have left it in the denominator because it would have ended up being a u substitution. Because I'd let u equal the natural log of y, and my du would be 1 over y, which is right there. Since it's not 1 over y to the first, I'm going to bring it up to the top because I'm looking at doing some integration by parts here. So integration by parts is the way to go. And for this integration by parts, should I be letting u equal the natural log of y or the y to the negative 1/2? And you all said something, and my hearing is not great, so I'm going to assume you all said the right thing, which is the natural log of y. Because whenever you're doing integration by parts, if you have a logarithm, that is u, end of story. So u is natural log of y. dv is the rest, which is your y to the negative 1/2 dy. Usual things. du is equal to 1 over y times dy. v is equal to y to the positive 1/2 divided by 1/2 is multiplying by 2. Okay, I'm going to atypically not write this out as an indefinite. I'm just going to keep limits of integration. So watch how this is kind of terrible. So I got 8 over root 6, 8 over root 6 times my uv. So that's the natural log of y times 2 times the square root of y, evaluated between 9 and 81, minus the integral from 9 to 81 of v du. That's 2y to the 1/2 times 1 over y dy. This is why I don't like doing definite integrals with integration by parts without just doing the antiderivative first, because then you have to write this and that. It's just kind of... So when you're doing integration by parts, the whole point here is that that next integral gets simpler. But that doesn't mean you can just do it without doing something to it. Often it means you have to simplify it. So this 2y to the 1/2 times 1 over y, we should simplify that as 2 times y to the negative 1/2. And then we're going to integrate it. So we're going to get, and I guess we might as well start doing work over here. So we're going to get 8 over root 6 times, I'm going to plug in the 81 and the 9 here. So I got natural log of 81 times 2 times the square root of 81 minus the natural log of 9 times 2 times the square root of 9. Great. Minus, I'm going to integrate this. So the integral of 2y to the negative 1/2 is 2y to the positive 1/2 divided by 1/2 is like multiplying by another 2. Multiply by another 2. Evaluated from 9 to 81. Okay, this is not as terrible as it might have looked like in the beginning. So we have 8 over root 6 times 18 natural log of 81 minus 6 natural log of 9 minus, so here we should be a little bit careful, minus, we'll plug in the 81 first and get 4 times the square root of 81 minus 4 times the square root of 9. And then we could simplify this further, right? This should be 4 times 9, which is 36. This should be 4 times 3, which is 12. So at the end of the day, we get something awful like 8 over root 6 or 8 over 6 if it was actually this problem times 18 natural log of 81 blah, minus 6 natural log of 9 minus 24. Gross. Yeah. Leaking. Okay. Not much more to say there. It's terrible, but it's not the most terrible thing I've ever seen. If I were doing this for myself, I probably would have done the indefinite integral first, just the natural log of y to the eighth over the square root of 6y, done the antiderivative, and then gone and plugged in the limits of integration from 9 to 81. Look at the other integral on the board there, which is the integral from 0 to 2 of r cubed over the square root of 16 minus r squared. All right, this one I am going to take my own advice. Since it's not a straight shot, I know the antiderivative. I'm going to do the indefinite integral first, and then go back at the end and do the definite integral, plugging in the limits of integration. So we're going to look at just the integral of r cubed over the square root of 16 minus r squared. To me, this looks like it's probably a u substitution with a back substitution. We're going to let u equal the stuff inside the square root. It's not a great choice because its derivative isn't exactly there, right? We would have preferred for that to have been to like a 16 minus r to the fourth, because the derivative of r to the fourth would be, well, be negative 4r cubed, and we have an r cubed. We don't have that. It's not the ideal u sub situation. It's still a u sub. So it's not, no, it is, James. We're going to find du. It's equal to negative 2r times dr. Yeah. And I know people, so I'm very biased in how I like to do this. I would much rather say negative 1/2 times du is equal to r times dr, and then break this apart as the integral of r squared times r over the square root of 16 minus r squared dr. And then say that r times dr is going to become negative 1/2 du. But I know that lots of other people, not me, prefer to say we get this. Or just leave it as r cubed, but I already did it so well. And then just replace the dr with, well, dr would be equal to du divided by negative 2r. I don't love that. It's not my jam, but it still works. So then the r's cancel here. And you still end up with exactly what I was going to get, which was r squared times du over negative 2 over the square root of 16 minus r squared. Either way you do it should get you to the same spot. I just like doing it this way better. To me, it feels nicer. So then we still have some things to deal with, right? I will remind you all, u substitution is a translation exercise. You have to translate completely from the language of your original variable to completely the language of your substitution variable. So we can't have u's and r's. I have to have just u's or just r's. So I've got some u, and I did the right thing. I dealt with the dr interchange to du first, because that is always the first thing to take care of in a u substitution. But then after that, we have to deal with the rest of the things. So I know that u is equal to 16 minus r squared. So I'm going to have the square root of u in the denominator. I've got my du over negative 2 over there. Let's see how I wrote the negative 1/2 in the front. And then r squared is we're going to do the back sub. So I'm gonna add r squared to both sides and say u plus r squared equals 16, and then solve for r squared and get r squared equal to 16 minus u. There is no good reason to isolate r here. You should not say that r is equal to the square root of 16 minus u, because you have r squared, and that's what's getting replaced. R squared is 16 minus u. Now we divide each thing by the square root of u. So we have 16 divided by the square root of u, which is 16 times u to the negative 1/2, minus u to the first divided by u to the 1/2, which is u to the positive 1/2. And now finally we are ready to antidifferentiate this thing. I know it only took us forever. And we get 16 times u to the positive 1/2 divided by positive 1/2 is multiplying by 2. And then minus u to the 3/2 divided by 3/2 is multiplying by 2/3. Oh, I did the stupid one. No, it's not stupid. It's not stupid yet. So oh, sorry, you can't see that. Yeah. I should have been more aware and said, oh, I can just change my limits of integration. So I'm actually not going to go over and do this. What I'm going to do is I'm going to say, yeah, this is the integral from 0 to 2 still. This, I'm still got r's here. So I'm going to say this is still the integral from 0 to 2. But now here, when I've changed things to u, I'm going to change my limits of integration. So if u is equal to 16 minus r squared, r equal to 0 means u is going to be 16 minus 0 squared, which is 16. R equal to 2 means u is going to equal 16 minus 2 squared, which is going to be 12. So my limits of integration should be kind of terrible. 16 on the bottom, 12 on the top. It's perfectly okay that those are out of the typical order we'd like them to be in. We just leave it as is and deal with it. Or if you really, really wanted to, although I don't usually recommend doing this, you could interchange these and make that a positive 1/2. Right? If you change the order, it just changes the sign. That'd be perfectly fine to do. Not really necessary. And this one's going to be kind of gross because 12 is not a number you can take the square root of nicely. So we end up getting kind of the terrible, blah. Yeah, you get negative 1/2 times 32 times the square root of 12 minus 2/3 times 12 to the 3/2 minus 32 times the square root of 16, which is 4, minus 2/3 times 16 to the 3/2, which is 8. Kind of gross. But it is what it is. We've seen worse, right? We definitely have. Questions about this? Okay. It is important, right, that when you do, if you do, and I do think this is the better way to take care of a u sub for a definite integral is changing limits of integration. We do have to keep track of which one goes where, right? When r was equal to 0, which was on the bottom, that corresponded to u equaling 16, so 16 had to go on the bottom, and which I didn't actually write in. Sorry about that. I should have written the 16 here and 12 here and a 16 here and a 12 here. Yeah. So make sure that they correspond to whichever one they actually correspond to. Yeah. Like from here to here. So what I did was I said 16 minus u over the square root of u is really 16 over the square root of u minus u over the square root of u, which is 16 over u to the 1/2 minus u over u to the 1/2, which is 16 times u to the negative 1/2 minus u to the first divided by u to the 1/2 is u to the positive 1/2. That's how we got there. All right. Moving right along. This fish, okay. Some word problems. Yeah, I guess I should write down all the words. A fish. Okay, let's write down the pertinent words. Let's read this and write down what's important. A fish starts life with a length of 3 centimeters. So if I'm saying that L of T is the length of the fish at time T. Oh, except we use A instead of T here, so let's use A, which is I think is silly, but whatever. So the length of the fish at time A is the length of the fish at time A, where A is measured in years, I believe. And then they're telling us that the fish starts its life with a length of 3 centimeters. So that means we can interpret that as L of 0 is equal to 3 centimeters. And that is an A, believe it or not. And then we're also told the fish has a maximum length of 31 centimeters. Okay, we'll talk more about that in a minute. So the max length is 31 centimeters. And then they tell us that the growth rate is 28 e to the negative a centimeters per year. So what that means for us that's not the function, right? That's not the length at time A, that's the growth rate at time A. And when we talk about a growth rate or a rate of change, we're talking about a derivative. So they're telling us not what the function is, but what the derivative of the function is. So they're telling us here that the derivative of L with respect to A is equal to 28 e to the negative a. Or if you prefer, you can write L prime of A, but I do think this type of notation is usually better for these problems. What is the average length of the fish over the first 5 years? You want to know the average length over the first 5 years. Cool. So to find the average value of a function, you need to take the integral of it over that interval and then divide by the length of that interval. And really, it's literally just it's the average height of the function. Like there's no better words to describe what we're trying to describe than what it actually is called. But to do that, you have to know what the function is. So we're going to take our derivative and solve for the function. We're going to solve this differential equation. So to solve dl dA equal to 28 e to the negative a, that means L as a function of a should be the antiderivative of 28 e to the negative a. If we anti-differentiate that, we get negative 28 e to the negative a, or it's actually 28 e to the negative a divided by -1, but let's write it more simply. So that's going to be negative 28 e to the negative a plus c. I feel like they've given you too much information here, to be honest. Like not too much, and it's not going to work. Just like you don't actually need to know both that it starts with a length of 3 centimeters and has a max length of 31. Knowing either one of those would be enough to find c. Let's pretend. Let me think about this for a second. Make sure I'm not saying something really stupid. Let me really double check. Yeah, no, this should be fine. Okay, yeah. Let's pretend they didn't give us this piece of information. We don't have that. All we have is this. What does that mean mathematically? The maximum length of this fish is 31 centimeters. Well, it means as time goes on and on and on and on and on, assuming the fish, it's actually kind of silly, but we're assuming the fish like lived forever, probably kind of dumb. If you took the limit as a goes to infinity of your function, it should equal what? The maximum possible length. So we can use that piece of information to find the constant c here. So this is our function, L of a. We're going to say is the limit as a goes to infinity of negative 28 e to the negative a plus c should equal 31. But I'm not going to write the 31 just yet. So I want to point out that this is equal to the limit as a goes to infinity. I never like e to the negative infinity. It's not my favorite thing. So I'm going to rewrite this as negative 28 over e to the positive a. And then I can see that as a goes to infinity, e to the a also gets infinitely large, and 28 divided by something infinitely large is infinitesimally small. So this 28 over e to the a is going to go to 0, and you're going to get 0 plus c, which is c. And then that should be what the limit is, which we just found out was 31. So that's the way you could find that c is equal to 31. Or we could have used the fact that L of 0 was 3, plugged in 0 for a, got negative 28 plus c equal to 3, and then c would have been 28 plus 3, which is 31. Same number. Great. That's only half the battle, though. So now we found the function. L of a is negative 28 e to the negative a plus 31. Now we have to find the average value. So average value of L of a on the interval from 0 to 5 is going to be 1 over 5 minus 0 times the integral of from 0 to 5 of L of a. Very generic. The whole area or the whole integral divided by the length of the interval. Something to think about here, just in general. So if I said velocity was the derivative of position, would you all be okay with me saying that? Like that seems reasonable to you? And acceleration is what? Acceleration is the derivative of velocity. And I want to point out that typically position, I'm just going to pick units, might be measured in feet. Velocity, if we're using feet for position, might be measured in feet per second. And acceleration might be measured in feet per second squared. The thing I want, equals is terrible here. Apologies for the notation. What I want to point out is every time you differentiate with respect to a certain variable, in this case, time, right? You differentiate with respect to time, you're essentially dividing by another unit of time. So positions measured in feet, and then the rate of change of position is feet per second. And then the rate of change of velocity is feet per second per second. Every time you differentiate, you're including another per whatever thing you're differentiating with respect to, oftentimes in these biology examples. So when you anti-differentiate, kind of doing the opposite. Instead of dividing by another unit of time, you are kind of multiplying by another unit of time. So what's happening here is you're taking your length function, which is measured in centimeters, and you're essentially taking that length and multiplying it by an amount of time, which seems kind of weird, right? Length times time, okay, whatever. But then over here, you're going to be dividing by a unit of time as well. So the unit still makes sense, right? You're going to get a length multiplied by a time divided by a time, so you're still going to get a length, the average length. But I really just wanted to say that because it's something that comes up a lot. A lot, maybe an oversell. It comes up somewhat, and that you should be thinking of, yeah, when you integrate, you're kind of multiplying by the units of the variable that you're integrating with respect to. Just like when you differentiate, you're kind of dividing by the unit that you're differentiating. Anyway, carrying on, actually doing the problem here, we get 1/5 times the integral from 0 to 5 of our function, negative 28 e to the negative a plus 31. We anti-differentiate. We get positive 28 e to the negative a plus 31a from 0 to 5. We plug in 5, we get 28 e to the negative fifth plus 31 times 5, which is 155. Minus, we plug in 0, and you get 28 e to the 0 plus 0. And if you wanted to simplify this a tiny bit, the only thing I would really do is write it as 1/5 times 28. I like 28 over e to the fifth, it's just my preference. And then 155 minus 28 is 127 centimeters. Whatever that terrible number is. Cool. I should ask, have you all been doing any survival and renewal problems? Okay, yes. So let's do, whoop, drop papers. Let's do at least one of those. And then we can look at some volume. Volume. I'm sorry, where'd you go? Papers. Blood flow, blood pressures. Yeah. It's probably only taking me like 5 years to memorize this formula. I think I've actually finally memorized it, but you should not memorize it. It's a formula that you should either look up or should be given to you. I don't think anyone's going to ask you to memorize the survival and renewal function. But let's look at, let's look at an example here. So here's the deal. Survival and renewal. So here are what the things mean. Initial population is P naught. We are adding people or animals or new members is actually what we say. We're adding new members at a rate R of T. And S of T is the percentage of the population surviving T years from the present. So here's our formula. The population at time T is equal to S of capital T. Now be careful here. I should also point out, and then, yeah, capital T is typically the amount of time. So P of little t, the population at any time T, is S of capital T, the number that have survived capital T years, or the percentage times your initial population, plus the integral from 0 to capital T of S of capital T minus little t times R of T dt. That's your survival and renewal function. All right. So most of this is just figuring out what all the things mean and then jamming it into this formula and maybe having to do some terrible integration, maybe not. Sometimes the integration is not so bad. So let's look at the following setup. And I don't want to I don't want to try to cram all this in this little space here. So let's say we have the following. A population of insects currently is 22,500 and increasing at a rate of R of t equal to 1,225 e to the 0.14 t insects per week, right? It should be a rate of change, so it should be a number of things per an amount of something. If S of t, S of little t, is equal to e to the negative 0.2 t, where t is measured in weeks, how many insects will there be after 12 weeks? So the first thing I would do after reading all this garbage is write down what these things are. So I'm going to say P naught, my initial population is 22,500. I'm going to say that S of little t, well, they told me what S of t, so I probably don't need to write these down again because they're right there. But what else do I need? I've got P naught, well, I should say I've got P naught. I need capital T. So capital T is the amount of time, which is 12 weeks. And I guess I could write down what these things are as well. So I should say S of capital T is S of 12, which is just going to be e to the negative 0.2 times 12, which is e to the negative 2.4. And then, more annoyingly, S of capital T minus T is S of 12 minus T. So when we plug that into our survival function, we're going to get e to the negative 0.2 times 12 minus t, which I don't really want to write out like that. I want to rewrite it as e to the 0.2 times t minus 2.4, or even better. No, not even better. Great. I think I have all the pieces. Let's jam them into this terrible formula. So we have that P of t equals S of t, which is e to the negative 2.4, times P naught, which is 22,500, plus the integral from 0 to 12 of S of t minus t, which is this thing here, e to the 0.2 t minus 2.4, times R of t, which is this terrible garbage here. Sorry, I speak so poorly of these integrals. They're beautiful integrals. They're not garbage. Don't want to hurt their feelings. Okay, so let's make this easier. We should certainly rewrite this as, and I'm just writing things kind of how my preference, I would write this as 22,500 over e to the positive 2.4 plus, watch what I pull out of this integral here. I'm going to pull out the 1,225. I'm also going to pull out the e to the negative 2.4. I'm left with the integral from 0 to 12 of e to the 0.2 t times e to the 0.14 t, which I could simplify as e to the 0.34 t. And then we're almost done. At some point, you're going to get out a calculator and actually estimate this thing or approximate this thing. But here you're going to get 1225 over e to the 2.4. And then we're going to integrate e to the 0.34 t. This is why we talked about those mini u substitutions. I don't want to take the time to write u equals 0.34 t and du equals whatever it's equal to. I just want to know that e to the something times t has an integral of e to the something times t divided by that something from 0 to 12. And I think we've done enough. I think you can do the rest. So they're kind of gross, but it's really just an extended plug-in chug, right? And yeah, sure, the integral might be harder. Sometimes this integral does require integration by parts or something a little more complicated, but for the most part, these problems are just, here are the things, do it. There is one example, which I don't really want to do because I should talk about volume for a second, but just let me see if I can find it here. Nope, I don't see it. Yeah, I guess I'll come back to that next week. I just remember there was one. Oh, yeah, is it this one here? No, it's not. Okay. There was one problem last year during a quarter where one of the problems was like this kind of survival new, and the question was kind of like how much do you have to be administering so that the amount of concentration in the bloodstream remains constant? Does that sound familiar at all? I see a few shit. So we can talk about that next week if we need to. We're in office hours. I don't remember how to set it up at the moment, but it was a little tricky to set up. But then once you set up, it's like, oh yeah, things work out just fine. Volumes. Sure, that one looks all right. Those are, yeah, both fine. So let's do one basic example of a volume, and then we'll try to tackle those two. Let's look at this. Let's say we want, and yeah, okay, they're both volume. So we're going to start off by finding the volume of the solid. So many words formed when rotating, or I should say when the region bounded by, I'm going to pick slightly different numbers here. Y equals x squared, x equals 0, and x equals 3. Sorry, y equals 0, not x equals 0. Apologies, that'd be terrible. Is revolved around, we'll start with the typical x-axis. And I can't stress enough, if you want these to be not hard to do, you have to draw the region. End of story. You have to draw the region. I'm gonna say it 5 more times. You have to draw the region, 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 you have to draw the region. You can do it without drawing the region, it's going to be harder. I'm gonna say it one more time. You have to draw the region. Okay, I've said it enough. Please draw the region. It's going to make life easier. I just cannot say it enough times. So let's draw the region. So y equals x squared looks like this. Y equals 0 is your x-axis. And x equals 3 is this line here. And the region should be the thing that is bounded by all of your boundaries. So in this case, it is this not quite triangular looking region here. Cool. And then, and let me just make sure, should be the case, but your teacher should only be talking about the disk/washer method. No one should have said anything about the shell method. If someone said something about shell method, let me know. They shouldn't be talking about it. Okay, so since we're only talking about the disk/washer method, I would next recommend in your region drawing a skinny little rectangle, which I usually call a vertical strip, perpendicular to your axis of rotation. Always perpendicular, never parallel. Shell is for parallel. We're not doing shell. So here, since my axis of rotation is the x-axis, I'm going to draw a vertical strip like this. And then what's happening is we're rotating this region around the x-axis. And I'm specifically focused on what happens when I rotate this little strip around the x-axis. So when I rotate that little strip around the x-axis, I get something that is disc-shaped. That's why it's called the disc method. Because that little thing looks like a disc. And the volume of that disc is just the area times the thickness. That shape is a circle. In fact, all right, we've got this little leg. I've just rotated the thing around. You see that okay? Let me zoom in a little bit. Cool. The area is the area of a circle. The thickness is the width of your strip, which I typically think of as dx, a small change in x. You can write delta x if you wanted to. I like dx because dx is what's going to end up in our integral. Okay, but then we actually have to figure out what the radius is. And here's the thing. The radius depends, right? That's the radius right there, how far away the circle, the points on the circle are from your center. But if I draw my strip here, my radius is a lot shorter, right? Over here, if I drew this little strip over here, my circle is much, sorry, sometimes my drawing skills are not great. You all paid a lot of money for your book. There should be some good pictures in there. I encourage you to look at them. So the point is the radius is almost always a function of the variable we're talking about. And it's usually just whatever the top function is. So here, my radius is just this upper bounding function. So this is going to be pi times my radius, which is x squared times dx. That's the volume of one disk, or as I like to think of it, it's the volume of a slice. But now I want to add up all the disks. Volume. That's the volume of one disk. Now I want to add up all the volumes of all the slices. And how do we add up all the volumes? We integrate. Just like before, we talked about like adding up a bunch of areas of rectangles and then taking a limit of that and getting the integral. Same idea here. We're adding up a bunch of volumes of slices, and then we're not actually going to write the limit. Say like, yeah, if you take the limit, it's the whole same thing. You get the volume of the shape. So the total volume is going to be the integral from as far left as 0 to as far right as 3 of pi times our radius squared dx. And I do think about the little strip I've drawn being able to slide as far left as 0, although it'd be like really, really short, like 0, to as far right as 3. So I think about having a strip as far right as over here, strip as far left as over here. And then the rest is pretty straightforward. And usually, most of the time, not all the time, most of these integrals are not too terrible to compute. Like they're usually moderately straightforward. So we're going to get, I would bring the pi out in front, from 0 to 3 of x to the 4th dx, which is equal to pi times x to the 5th over 5 from 0 to 3. You plug in the 3, you get 243 times pi over 5. You plug in the 0, you get 0. So that is what we get. You probably be fine just to write 3 to the 5th. You don't have to know that 3 to the 5th is 243. But it's not that hard to do, right? 3 to the 4th is 81. Multiply by 3, it's 243. Okay. Yes. What if we went around the y-axis? Dun, dun, dun. We draw it again. Same region. This is, whoops. This is still the line x equals 3. This is still the line y equals 0. This is still the line the curve y equals x squared. And I should point out that this point here is x equals 3 and y should be what? Oh, sorry. I forgot I was super zoomed in. I'm so sorry about that. Sorry. What should y be if x is 3? And it's on this curve, y equals x squared. 9. And we're going to need that 9. I should zoom back out a little bit here. A little too zoomed. Okay. So just like I was saying before, when you're trying to find the volume and you're rotating around an axis, this time the y-axis, you want to draw your strip perpendicular to the axis of rotation. So now I'm going to draw a horizontal strip. And that's always the case. If you're going around a vertical axis, your strip should be horizontal. If you're going around a horizontal axis, your strip should be vertical. Always. So then if I think about rotating this little strip around, well, now it's going to look like not quite a disc, but a washer. And the volume of my washer is equal to the area of the big circle, which is pi times the big radius squared, minus the area of the inner circle that isn't there, pi times the little radius squared, all times your thickness, which in this case isn't dx, it is dy. Small change in y. I'll point out that is your small radius of the circle that isn't there, that you've subtracted away, and that is your larger radius of the circle that is there. Okay, so my larger radius, well, the larger radius is just 3, right? We're 3 away from the axis of rotation all the time for this larger one. My inner radius is variable, right? If I drew it up here, it'd be different than if I drew it down here. And now here's the trick question. What's the inner radius? Yes, it's a trick. It's not x squared. I mean, it is, but it isn't. I'm going to have a dy. That means my function has to be in terms of y, not in terms of x. So I have to take this y equals x squared and solve for y. Solve for x. Square root of y equals x. Technically, it's plus or minus the square root of y. But since we're on the right side here, right, we're not on the left side, should x be positive or negative? Definitely. So it's got to be the positive square root of y. Be careful though. Sometimes it's the other side. It's the negative part. So just make sure you're looking. That's why you should graph it. Graph it, graph it, graph it. Graph, graph, graph. So then this is going to be pi times the larger radius squared minus pi times the smaller radius squared all times dy. And then we're going to find the total volume by taking the integral from as low as my strips can go, which is y equals 0, to as high as my strips can go, which is y equals 9. Factor out the pi. You've got 3 squared minus the square root of y squared. Which is not too terrible. I mean, as far as integrating this, it's pretty straightforward. And then we get pi times 9y minus y squared over 2 from 0 to 9. That's going to be pi times 9 times 9 is 81 minus 81 over 2 minus 0 minus 0. You know what 81 minus half of 81 is? Half of 81. No need to get a common denominator here. Just use some common sense. I feel like there's a funny thing to say there, but I can't quite think of it. So yeah. Who needs common denominators when you have common sense? How about that? Yeah, sure. All right. I think we can hit one of these two here. Yeah, let's look at the natural log of x one. That one seems a little bit wilder. So, oh yeah, yeah. Yeah, okay, great. So find the volume of the solid obtained by retaining the region bounded by y equals natural log of x, y equals 2, y equals 3, and x equals 0. Let's just draw it. So y equals natural log of x has an x-intercept of 1. It looks like this. Might be exaggerating it a bit. No one cares. And then we have y equals 2. We have y equals 3. And we have x equals 0, which is the y-axis. So we're looking at this region here. It's got to be bounded by all of our curves, and it is. And we're unfortunately going around the x-axis. Boo. But it's a good example, so you should do it. Here's why this is boo. I'm going to draw a vertical strip, right? Because I'm going around a horizontal axis, so I have to go draw a strip that's perpendicular. And the problem is, depending on where I draw my strip, the upper and lower bound might change. So if I draw my strip somewhere like here, the outer radius is 3, the inner radius is 2. That's not going to be that terrible, actually. But if I draw my strip over here, the outer radius is 3, and the inner radius is now the natural log of x. So what that means is we have to break this up as 2 integrals. There is literally no other way to do it. You have to break it up as 2 integrals. And we're going to break it up right here, where y equals 2 meets y equals natural log of x. So if natural log of x equals 2, then x is going to be e to the second power. So that point there is e squared comma 2. Okay, so for this one, we're going to have x going from 0 to e squared. And it's going to, whoops, that's a 2, by the way. And it's going to be pi times your outer radius squared minus your inner radius squared. That's fine. That's just going to be 5 times e squared times pi. Easy. The second part's a little bit suckier. So the next part, you're going to go from here to there. This point is probably e cubed comma 3. Right, because if y is 3, then x has to be e cubed. So you're going to go from e squared to e cubed. And it's going to be pi times, okay, in this region here, my outer radius is still 3. My inner radius is natural log of x squared. Okay, how much time we got? Okay, here's what I would do. Yeah. So I would do a couple things to make my life a little bit easier. So I point out that this is pi integral from 0 to e squared. 9 minus 4 is 5. And actually I'm going to break this up as pi integral from e squared to e cubed times 9 minus pi integral from e squared to e cubed natural log of x squared dx. These two things are easy, right? And so I will just point out, I don't think I've said this before, when you have an integral of a constant over, and it's a definite integral, you just get that constant times the length of your interval, right? You would integrate this, you get 5x, and you plug in e squared minus 0. So this part here is going to be pi times 5 times e squared minus 0. I know you don't need to write minus 0. This part here, same deal. It's going to be pi times 9 times e cubed minus e squared minus pi times whatever this trash is. And that's where I would say, okay, off to the side, let's do the integral of the natural log of x squared. And I'm not thrilled about that. I'm really not thrilled because it's going to take integration by parts twice. You're first going to let u equal the natural log of x squared. Your du is going to be, or my dv is going to be dx. My du is going to be 2 natural log of x times 1 over x dx. My v is going to be x. We're going to rewrite this as u times v minus the integral of v du. And when we do v du, we get x times 2 times natural log of x times 1 over x dx. The x and the 1 over x get to cancel out. So then we're going to get natural log of x squared times x minus 2 times the integral of natural log of x. And then you integrate by parts again. Now, you probably, in my opinion, are going to do the integral of natural log of x enough times that you should just memorize it. So I will tell you that the integral of the natural log of x is x times natural log of x minus x. And then you can go back and say, great, that's what this piece is going to be. So it's going to be x natural log of x squared minus 2 times x natural log of x minus x. Holy shit. And then you go from e squared to e cubed. Terrible. But no, terrible. There's no lying about it. So this problem would have been a much nicer problem if it had been rotating around the y-axis, because then, oh my God, look how much, I know we're out of time. It's 2 o'clock, but I'll just point out, if you're going around the y-axis, then your function would have been e to the y, which is much easier to integrate, and the limits of integration would have been from 2 to 3. I would have been e to the y squared. So I just want to point out here, because I think it's worthwhile, if this was around the y-axis, you would have been doing pi times the integral from 2 to 3 of e to the y squared dy. And e to the y squared is just e to the 2y, which is super easy. So I feel like someone might have accidentally meant to write that around the y-axis and accidentally wrote around the, not you all, like the person who assigned that might have meant for it to really be, I hope they really meant for it to be around the y-axis, because that would have been a much nicer problem. All right, that is all the time we have for today. I'll see you on Monday. I got office hours in the usual spot.